Okay, so we come to the final part of the proteins lecture. Look at some examples from food. So bread protein. Bread's an important example of a food whose structure depends on proteins. This discussion refers to leavened bread made with ingredients typically such as those shown above. That is to say, bread where yeast is used to cause raising. Albumins and globulins are important bread proteins in terms of nutrition, but they don't contribute significantly to raising. Gliadins and glutenins react during the process of kneading to produce the elastic protein mass called gluten, which gives bread its elasticity and allows it to trap carbon dioxide. There's an issue, of course, that many people are gluten intolerant. Again, this is what happens during kneading. The two proteins come together to produce this elastic protein. So the kneading is a process of preparing the bread so it can rise, usually done in two stages. The two proteins form thiol crosslinks, that is to say sulfur-sulfur bonds. Oxygen from air is added to the mixture during kneading, and that is required. For more on bread making, click on the formula down here for the action of yeast. I'll take you to the science of bread making in terms of fermentation. So there's lots of interesting stuff there. But basically what this image is showing is that as CO2 is generated by yeast, the elastic proteins, the glutens, expand, trapping carbon dioxide, raising the bread. Bread without gluten is possible. There are many gluten replacers available now, which is good, since, as mentioned, some people are gluten intolerant, and there's some good quality gluten-free breads out there now. Didn't used to be the case. These are some we've done in the past in the lab, and if you look at the difference between normal bread and the 70% gluten-free flour, it's a very different product clearly, and the 70% gluten-free flour was quite unpleasant. I say there's some very good commercial examples now available. Cheese is another good example of a food where protein is important both for nutrition and structure. We're not going to look in detail at cheese making, but many resources are available if you're interested. Just search online. Milk composition. This is a non-water components of milk, of course. Most milk is, as you know, water. But it contains, in terms of non-water content, it contains about 26% of protein and around 31% of fat. Depends on the source of the milk, obviously. And this only refers to animal milk, of course. Again, you can find details of the fermentation involved in cheese online. It's interesting, but it's not really part of this discussion. What essentially happens is that microbes use lactose as the energy source. They ferment, that is, they grow in number, producing lactic acid and carbon dioxide by the formula we saw a little bit earlier on. So rennet, get back to proteins. Rennet is a group of enzymes used to coagulate milk. That is to say, take milk to form the thick curds and the liquid whey. A number of enzymes are involved in complex ways, including the proteolytic enzyme chymosin. Traditionally, rennet used to be obtained from calves' stomachs, or in some cases just by dropping slugs into the milk. Currently, it's usually obtained from microbial sources. If you click on these links, it'll take you to a commercial source of where these things are obtained. Main protein in milk is casein. That's a protein that makes milk white. It's a globular protein arranged in the way we discussed earlier. That is to say, with the hydrophobic elements on the inside and the hydrophilic elements on the outside. It's also studied with calcium atoms as well. So chymosin hydrolyzes a single bond in what we call kappa casein, which then can't form micelles. The structure we saw in the previous slide was a micelle in effect, or a micelle-like structure. So it precipitates out the solution as curds. This can also be done by lowering the pH by adding acids such as vinegar. It's a slightly different process. So a little bit more detail. Rennet splits kappa casein into small macropeptides which remain dissolved in the whey, and para-kappa casein, a form of casein which can form micelles, so the other forms it's free to cross-link and precipitate out. As mentioned, these days bacterial chymosin is used, marketed as vegetarian rennet, and increasingly other enzymes such as proteases from fungi and porcine pepsin, that is pepsin from pigs. They have the advantage they do not cause excessive hydrolysis of other proteins, though the latter, of course, is not vegetarian. So, we'll finish with some comments on protein analysis. There's a number of ways to do this. Kjeldahl method is widely used, often in automatic systems. It allows a measure of protein quality based on nitrogen content. This isn't perfect, since it measures all nitrogen foods, including non-protein sources, and a calculation is normally done to convert the result obtained into an amount of protein nitrogen. As we can see, this approach, just looking at nitrogen, can lead to serious health and legal problems, as illustrated in recent terms. These are pretty extreme conditions. We're taking sulfuric acid. We've got a couple of catalysts in there. Copper, potassium sulfate, which increases the boiling point of sulfuric acid to 350 degrees centigrade. And this converts all the protein nitrogen into inorganic nitrogen as ammonium chloride, NH4Cl. Excess sulfuric acid is then hydrolyzed with sodium hydroxide. The rest of the apparatus is assembled and ammonia is boiled off as a distillation. This distills in a collecting flask and is then subsequently titrated with something like 0.1 molar hydrochloric acid. For more details on calculations, see this link, which has a lot of good stuff on Kjeldahl reactions and Kjeldahl calculations. Well worth having a look at if you're interested. So when it all goes wrong, this here is melamine, a molecule which, as you can see, contains a lot of nitrogen. A scandal arose when food was found to have been deliberately contaminated with melamine to increase its apparent protein content. There's one example from Cadbury's food and also in other products, which we won't talk too much about. See the news reports for more information if you're interested. This is just a calculation of nitrogen content for melamine, so it's quite high, and it was added to artificially increase the nitrogen content and therefore the alleged protein quality of milk in a number of dairies in China. This was a serious issue, as we can see by the numbers here. Melamine precipitates in the kidneys, causing potentially serious illness or even death. And so the problem was that Kjeldahl method only distinguishes nitrogen. It doesn't distinguish between non-protein and protein nitrogen. That just appeared. Yes, the issue arose in China, said, and the authorities took a very serious view indeed over this. I will say nothing about that. Okay, so that's all, folks, and that completes the 3 protein lectures. Thanks for listening.